Hello everyone! We are very happy to be able to participate in this conference and to make our presentation despite the current events, and we would like to especially thank all the people who made it possible to hold this conference despite the difficulties. Before getting to the heart of the matter, a few words to explain the context in which our research takes place on the Ertel Meridian Circle of the Neuchâtel Observatory. Our work is a part of a research project on the history of the Neuchâtel Observatory led by Professor Jeanneret of the University of Neuchâtel. It is a part of my PhD project entitled The Neuchâtel Observatory 1858-1958 Cultures of Precision, Technical Devices, Places, Actors and Scientific Activities. One of the main lines of the research is the analysis of the material culture of the observatory in order to examine the role of scientific instruments and spatial configuration in the constitution of and maintenance of an astronomical culture of precision at the observatory. Within this framework, Romain Jeanneret, a conservator, participates in the project and provides its expertise. This collaboration between an historian and a conservator is one of the specific points of our project. Therefore, this paper includes two voices. Moreover, this paper presents a work in progress, so we will be very thankful to hear your remarks, experiences and possible questions to help us move forward. The Ertel Meridian Circle was of crucial importance in the establishment of a culture of precision at the observatory when the institution was founded in 1858. For more than a year, it occupied the attention of the institution director Adolphe Hirsch. The exchanges between the manufacturer Ertel and Sohn and the institution make it possible to follow the development of this instrument according to technical constraints and scientific needs. The Meridian Circle is also at the origin of the creation of the data transmitted by the observatory and is, in this respect, a key element of the time service. To introduce you to the Meridian Circle and to understand the issues surrounding it, we will first provide a brief historical context of the creation of the observatory. Next, we will present the constitution of the Meridian Circle based on the sources at our disposal: correspondence, various illustrations, photographs and plans of the instrument. Finally, we will discuss the day-to-day operation of the observatory to see how the Meridian Circle is used, its errors studied, and the influence that the change of the method of meridian observations has on the observatory's practices. The creation of an observatory in the canton of Neuchâtel in Switzerland emerges from the wish of the watchmakers to have a means of controlling their products and to establish a high-precision watchmaking industry. In 1855, after the Universal Exhibition in Paris, a report by Neuchâtel delegates asked for a state observatory to guarantee the neutrality of product certifications and to develop the watch industry. After several preparatory studies, a young astronomer was commissioned to elaborate the project in more detail, Adolphe Hirsch. Adolphe Hirsch was born in Halberstadt in 1830. He studied in Berlin with Johann Franz Encke, then worked with Carl Littrow at the Vienna Observatory before being hired in 1858 by Leverrier at the Paris Observatory. Hirsch thus has experience with different observatories and knows examples of instrumental configurations. On his way to Paris, Hirsch stops in Neuchâtel to write his report. In this document, he advises the Neuchâtel authorities to set up an observatory concentrating on a specific activity, the scientific determination of time as he mentioned in his report. I quote, "You should set up the observatory in such a way that it has the strictly necessary means, but at the same time sufficient to be able to determine the time in a perfect way, to give your watchmakers a safe and easy means of checking their regulators every day, to supply the marine chronometers with accurate setting tables, and finally, to produce irreproachable astronomical observations. Hirsch, who was approached to head the new observatory, made sure that the building was configured to house the scientific instruments and was in charge of making contacts with scientific instrument manufacturers in parallel with his work at the Paris Observatory.
To carry out the order of the Ertel Meridian Circle, Adolphe Hirsch benefits from his experience and that of some of the astronomers of his time. His reading of astronomical treatises and magazines, such as the Astronomische Nachrichten, was also a valuable source of information for him, as it is for us today. Having another view of the state of the art of science and technology for Meridian Circle in the 19th century gives us a better understanding of the issues at stake. During our research, we conducted a non-exhaustive review of the Meridian Circle in the mid-19th century. Which manufacturers, dimension, materials, technical solutions, etc. were available at the time. Here are two examples with the Repsol Meridian Circle of the Pulkowa Observatory and the Ertel Meridian Circle of the Roman College. These models are close to what is chosen for Neuchâtel instrument. Like Struve in Pulkowa, Adolphe Hirsch is actively exchanging with Ertel in order to build a meridian circle that fits the mission and budget of his observatory. These rich exchanges allow us to follow the evolution of the conception of the meridian circle. Adolphe Hirsch's first request refers to an Ertel catalogue that dates from 1853, although we have not specifically found this source. The catalogues published before and after provide information that allows us to have a good idea of the requested project. Hirsch is interested in a meridian circle which has intermediate characteristics between two models in the catalogue. This choice between two models can be explained by budgetary constraint. Hirsch wants an instrument with as much aperture as possible, but he does not necessarily have the funds for an upper-class model. He then asks, 3 feet in diameter of the circle, 54 inches of focal length, 48 lines of apertures, and a micrometer with 5 vertical wires. He also requires an accuracy to the tenth of a second and a constant instrument. This last characteristic is fundamental for a meridian circle whose error prediction is at least as important as the theoretical accuracy. Within a few days, Ertel sends back a first generic draft with 2 models regrouping different possible options. Hirsch then validates some proposals such as a reversing carriage, which is used to alternate the forces on the pivots and the bending of the optic tube. The counterweight system, the number of microscopes, and the presence of a single reading circle were also parts of the discussions. After a few exchanges, the dimensions of the meridian circles are revised upwards. As the modifications are important compared to the first draft, Hirsch asked for a new technical drawing. This new version fixes certain options taken by Adolphe Hirsch and serves as a basis for the order of the meridian circle. The aperture increases to 56 lines and the focal length to 72 inches. This dimension will not change anymore. However, as it took a year between the order and the delivery, exchanges continue and options are still discussed and specified. Some specific aspects are the subjects of bitter negotiation and differences between the astronomer's scientific preferences and the technical possibilities and experience of the instrument manufacturer. This is the case, for example, with the reticle field illumination system where Hirsch insists on integrating the Airy system from Greenwich with a prism device inside the eyepieces. Ertel is against this solution and proposes instead the so-called Starke system with lighting from outside. The manufacturer will impose his choice because of the lack of space near the eyepieces. In addition to these changes, Adolphe Hirsch is adding a new instrument which will require the modification of parts of existing instruments as well as the daily practices of the determination of the time, the printing chronograph. Until the middle of the 19th century, the main method used for astronomical time determination was the so-called eye and ear method. Through the telescope, the astronomer observes the transit of a star on the local meridian and compares it to the time given by a sidereal clock. As the moment of passage of star, as the moment of transit of a star is known in advance by ephemerides, it is then possible to determine the advance or delay of the clock. In practice, the reticle contains several wires and the observer determines the star's transit for each of them by estimating the interval between 2 beats of the clock with an accuracy of about 1/10 of a second. With this technique, the reticle of the meridian instrument contains only 5 or 7 wires at most. Indeed, this practice requires a complicated and exhausting exercise of memorizing the seconds and determining the moment of passage for each wire. Now, let's look at the chronographic method. To illustrate it, we present what we call the operating chain of time determination used the early years at the Neuchâtel Observatory. Here are the 3 main instruments used for time determination: the Ertel Meridian Circle, the Wiener sidereal clock, and the Hipp's recording chronograph. The function of the chronograph is to print a mark on a strip of paper each time it receives an electrical impulse. The strip of paper runs at a known and regular speed thanks to a clockwork mechanism. It is then possible to determine the time interval between 2 pulses by measuring the distance between them. Each time the astronomers observe the passage of the star with his golden eye on a vertical wire of the reticle, he closes an electrical contact by his gold finger. This sends an electrical signal to the chronograph, which prints it on a paper strip. At the same time, the sidereal clock, set up with an electric switch, sends a signal every second which is printed parallel to the astronomical observations. By comparing the known instant of passage of the star with the second of the sidereal clock, it is then possible to determine the advance or the delay of the clock. Allowing the networking of the instruments after the addition of the chronograph requires some technical modifications on certain instruments. For the sidereal clock, the addition of an electric switch involves to review the balance of the mechanism. The meridian circle is also adapted to be used optimally with the new method. In addition to the setup of an electric key, the reticle is modified. Since the observer is no longer required to count and memorize the moments of transit, this allows the number of wires of the reticle to be increased from 5 to 21. This change of method has a direct impact on the accuracy of time determinations. However, the accuracy of a single bisection stays close to the accuracy of the traditional method. It is more the multiplication of the quantity of data produced that increases significantly the accuracy using statistical tools. According to Adolphe Hirsch, the accuracy of time determination of a transit is doubled. It is therefore mainly an improvement obtained quantitatively and mathematically. The follow-up of the conception of the meridian circle, letter after letter, allows us to find its state at the delivery in September 1859. A second graduated circle and 4 new microscopes for reading the graduations were added. This illustration, made once the instrument has been delivered, gives an idea of the final state of the instrument, which completes the contribution of the handwritten sources.
Like all scientific instruments, the instrument delivered is also not geometrically perfect. It is responsible for a certain number of errors during observation. It is therefore essential to identify and measure these errors in order to correct the data mathematically. Atmospheric conditions, manufacturing imperfections, and wear and tear affect the accuracy of the measurements obtained. All of this is constantly identified, measured, and incorporated into the data by formulas to reduce errors. Different types of errors can affect meridian observations, which we will not go into in detail here. The instrumental errors that are regularly checked are inclination, collimation, azimuth. Sights are thus installed and used to check the collimation of the instrument. Levels are used to check the inclination on the mercury bath for the azimuth. The observatory will continue to improve the accuracy of the data by advancing the technical devices and its observation methods. Following the introduction of the chronographic method, also known as the American method, the observer's reaction time becomes measurable. A reaction time between the instant of observation of the passage of the star in front of a wire of the micrometer and the instant of manual pressure on the electrical contact exists, which is called the personal equation. This time interval must be taken into account when determining the time to improve the accuracy of the data and to allow comparison of results obtained by different observers. It varies from one observer to another, but also for the same observer depending on his physiological condition. To better understand this phenomenon, Adolphe Hirsch is conducting research on the subject, assisted by Mathäus Hipp, who is developing a chronoscope to measure very short reaction times. A device is also installed on one of the observatory's sites to artificially recreate the passage of the stars and thus measure the reaction times of the operators. For a few years, Neuchâtel became one of the centers of physiological research on the personal equation as demonstrated by Jimena Canales and Henning Schmidtken. Once the instrumental errors are known and constantly checked, and the personal equations determines the Ertel Meridian Circle functions satisfactorily for 50 years, not without undergoing various changes which we will quickly review. Lighting is almost directly at the beginning supplied by gas and then electrified. Hirsch achieves his goal by switching from the starke to the airy lighting system with the installation of a prism in the eyepiece tube of the Meridian Circle. Replacement of the pivots and spider wires on the reticle. Numerous other checks and adjustments. In 1912, after more than 50 years of use, the instrument was placed in the Musée de l'Observatoire, a museum of which we have not found any trace or mention in the archives. With the exception of its optical part, which is recovered to equip its successor, the Meridian Circle manufactured by the SIC, the Geneva-based company for the manufacture of physical instruments, we do not know what became of the Ertel Meridian Circle. During the century in which the rotation of the Earth is used to determine time, the observatory seeks to remove the influence of human factor. The Bamberg instrument, here on the left, used as early as 1907, and the SIC Meridian Circle in the center, which replaced the Ertel Meridian Circle in 1912, are equipped with an impersonal Repsol micrometer. The photographic zenithal tube, the PZT, and the Donjon Astrolabe completely eliminate the influence of the human factor on data production. These last instruments conclude a century long before the introduction of atomic time completely changed the paradigm of time measurement. We thank you for your attention and we look forward to your questions.